Spring 2017 final time for MA 266. This exam features some of the easiest questions that we've ever seen on one of these finals, and additionally, one particular variation of parameters question that I'm incredibly glad this is the last time I will ever be doing it, unless they repeat it on the final. It's pretty brutal. Question 1, let's find the solution to this initial value problem. So if we take a look at what y prime is equal to here, we have a function of x over a function of y. So let's turn our y prime into dy dx and multiply this function of y up. 2y minus 6 is equal to 4x cubed plus 1. Let's multiply this dx over and integrate both sides. We will get y squared minus 6y is equal to x to the fourth plus x plus c. And what do they want us to do? They want us to solve for y in this case. So how can we do that? It's a little bit unclear because we have a y squared minus 6y, but really what we'll need to do here is complete the square. Let's find this value of c before we go do any of that. Y at 1 is equal to 2, so 2 squared, 4 minus 12, so negative 8, is equal to 2 plus c. So c is negative 10 over here. So what do we need to add to both sides to complete the square? Well, y minus 3 squared will be y squared minus 6y, that's good, plus 9. So let's add 9 to both sides. So we can say that this is x to the fourth plus x minus 1. We can take the square root, and since y at 1 is equal to positive 2, let's keep that plus or minus in there for now and add this 3 over plus 3, and then reevaluate to make sure that we're using the correct side of the plus or minus, even though we know that a is our correct answer. That's the only one with a constant of 3 there. So y at 1 is equal to 2. That will give us the square root of 1 here. Yeah, so we'll need to use negative 1 plus 3 to get to that 2, so 1 is a. We're finding the exact solution to this initial value problem, and well, no, sorry, y of t is the exact solution. We're finding y approximate of t, and we're approximating y at 3. We know that y at 1 is equal to 0, so we can approximate one step size above that, so y at 2 is approximately y at 1 plus our step size multiplied by y prime evaluated at this condition here. So we need to kind of rearrange this. We can say that y prime times t is equal to t plus 2y. We can divide that t out, get 1 and 2y over t right there. And that makes a little sense why we started with y prime, why we started it with y at 1 instead of y at 0, so we don't divide by 0 here and create some issues. So we're evaluating this at 1, 0. That will give us 1 here. So y at 2 is equal to 1, is approximately equal to 1, and so we can approximate y at 3 as what y at 2 is equal to, plus our step size multiplied by y prime evaluated at 2, 1. So that gives us 2. And so y at 3 is approximately equal to 3, so 2 is c. What is the largest open interval in which the solution to this initial value problem is guaranteed to exist? So always we have to divide out anything that's on y prime, or in general our highest order derivative here. So we can rewrite this as y prime plus ln t minus 1 over t squared over t squared e to the t minus 2, and that's equal to t minus 5 divided by sine t minus 4 times t squared. And we'll look for the discontinuities in this whenever, oh, we have a y here, by the way, whenever we get any undefined behavior. So t is equal to 0 is no good because of the t squared in this denominator. It's a little bit harder to see, but t is equal to 1 is also no good. So this natural log of the absolute value of t minus 1 will always have a positive value, which is great, but sometimes it's positive 0, specifically when t is equal to 1, and the natural log of 0 is undefined. So that's no good. And additionally, whenever this sine component here evaluates to 0, we have issues. So that will happen for t is equal to 4 minus pi and 4 and 4 plus pi. Because if t is equal to 4 at all, if we have 4 anywhere in there, that will subtract, we'll subtract 4 from it and we'll get 0, and then these pi's, the sign of 0 and the sign of pi, the sign of 2 pi are all 0. So those are the ones to think about. So let's make a number line down here with all of our discontinuities. We have 0, 1, and then 4 minus pi is 4 minus 3 and a little bit, so 4 minus pi sits over here, and then 4 plus pi. These are all the no-go zones. We see that our initial condition is for y at 3. That's going to fall right in here, and so the farthest left that we can go and the farthest right we can go define the bounds on our existence and uniqueness theorem guarantee for our solution existing, and so that gives us 1 and 4, so 3 is D. 4, let's identify the differential equation corresponding to this direction field here. So at y is equal to 0, we see an undefined, so infinite slope there. So we would expect our solution to be, dy dt, to be divided by some constant multiplied by y, because in that form, when y is equal to 0, or just in general, we want when at 0 for the denominator of our expression to evaluate to 0. Then what other behavior do we want? I mean, at this point, we already have our answer, which is a little too easy. We see that this 2y on the bottom is the only one out of all these expressions that will give us that undefined behavior at y is equal to 0. All of these other ones, see, a doesn't even have any issues with y is equal to 0. Here, y prime is just equal to 0 at 0. Here, y prime is equal to 0 at 0, and here, y prime is also equal to 0 for y is equal to 0. But making sure that this works for our other behavior that we want to see, if we plug in, let's say, positive 2, we want to get a positive slope, we will get 4 over 2, 1. And that's looking very much like a slope of 1 right there. Then at negative 2, we're seeing a slope of 0, which is exactly what we see over here. And then below that, let's choose negative 4. Negative 4 plus 2 over 2 times negative 4. That will give us a small but positive value. So 4C checks out for all of those requirements. 5, let's solve this initial value problem. So we see that we have things in a form on our right side that we can write as a rational expression of y over x. So we can say that dy dx is equal to x to the 4th over x to the 4th plus y to the 4th over x to the 4th over x y to the 3rd over x to the 4th. So rewriting this, and well, gotta be careful here. We're applying a substitution here where v is equal to y over x, and therefore dy dx, by the product rule, if you want to go work all that out, is dv dx times x plus v. So we'll do all that replacement. We get dv dx times x plus v is equal to 1 plus v to the fourth, all divided by v to the third. So we can subtract this y over and express it as minus y to the fourth, minus v to the fourth over v cubed, and add it into this rational expression that we already have going here, and that's just going to remove that y to the fourth. So now, what should we do? Let's multiply this v over, so we have v cubed dv, and then we'll multiply the dx over dx and divide the x out, so it goes over there, and we can integrate v to the fourth over 4 is equal to ln x plus c. So v to the fourth is equal to 4 ln x plus some other c, which just happens to be 4 times that original c, and then we can unsubstitute y to the fourth over x to the fourth, which I'll just go multiply right over. No, actually I won't do that. I won't do that at all. Let's take the fourth root before we unsubstitute, just to make things a little easier on ourselves. So v is equal to the fourth root of 4 ln x plus c. Oh, sorry about that. Keeping my sound on by accident. And okay, what else are we doing? Then we're just performing the unsubstitution. So y over x is here, and we can just multiply that in. So because y at e is equal to e, we can evaluate for our constant c here. So e is equal to e times the fourth root of 4 ln e, which is 4, and then we want this whole thing plus c to evaluate to 1. And so c has to be -3. C is -3. So we can plug that in, and we have our explicit solution there. We've gotten answer choice C, 4, 5. 6, let's find the solution to this thing. I'm feeling like doing some integrating factor. Let's divide 2t out from everything so that we can find our p of t, so we can integrate for our rho of t, etc., etc. So y prime minus 4 over 2t, so 2 over ty is equal to 2t cubed e to the t squared. I'm not sure why I got all off center there. And remember, the term that's on y is only called p of t so long as the coefficient on y prime is equal to 1. You got to remember that, because if you try to do integrating factor just using -4y, you will not get the correct solution. So we know that rho of t is equal to e to the integral of p of t, where p of t is this term on y there. So -2 over t dt will give us -2 ln t, so we get t to the -2. We also know that we can write y of t as 1 over rho of t, so t squared times the integral of rho of t, t to the -2, multiplied by q of t, which is our right-hand side term here after we've divided out everything, every term on our y prime. And that gives us 2 2t cubed e to the t squared dt. Combining some like terms here, we're left with 2t, so we can do a u substitution, and I won't even bother writing it out because this is just about the most textbook u substitution case in the world. We will get t times e to the t squared plus c, and this is t squared and y of t. We know that y at 1 is equal to 0. Let's solve for c. 0 is equal to 1 times e to the 1 plus c. So c must be negative e. Negative e. And so our solution is t squared e to the t squared minus e t squared. So 6 is a. 7, let's find the solution to this initial value problem. This is looking like an exact equation to me. We call this function m and this function n. And if my is equal to nx, those are the partial derivatives of m with respect to y and n with respect to x, then our equation is exact and we'll be able to solve it pretty easily. So my is 6x plus 2y, and is that equal to 6x plus 2y? Well, yep, it is. So now we'll take the integral of m dx, which is 6xy plus y squared dx, and we'll compare that with what we get for our integral of n dy, 3x squared plus 2xy plus 2y dy. We will get 3x squared y plus xy squared, and on the other side we get 3x squared y plus xy squared plus y squared. So overall, we have these two terms which overlap in both of our integrals, so we only count each one of those once, and we can add in this y squared, and we'll have the function whose partial derivative with respect to x is m, and whose partial derivative with respect to y is n. And that's why, by Clairaut's theorem, if we call this function psi xy, that mixed partial derivative must be equal to psi yx. That's why we can check these two to see if there is some overall function that has these properties. So in the end, we get 3x squared y plus xy squared plus y squared is equal to some constant c. And since we know that y at 1 is equal to 3, I'm going to shrink all this down so we have more space, and we can evaluate for this c. We get 9 plus 9 plus 9 is equal to c, so c is 27, and that matches everything else. So 7 is e. 8, we have an initial value problem here. We're looking for the limit, or which initial value has a limit as t approaches infinity of 1. So really what this is asking us to do is make a number line. Let's put down all of the places here where y prime is equal to 0. We have 0, 1, and 2. I didn't really construct this very well. And let's see which initial value will have this property. So whenever you get something like this, where you have something in here, y minus or plus something, and then that whole thing squared, the nice thing is that's always going to be a semi-stable solution. That's why there's only one value, one area that approaches 1 as t approaches infinity, because the other one will flow away from it. And that's just because, as we pass by this point, this component will not change sign, although it will go to 0 when we actually hit t or y is equal to 1. So all we have to do is plug in something here and plug in something here and see where they go. These arrows could easily be like this. We're not really sure. So let's plug in 0.1. We'll get a negative value times something that's always a positive value times a negative value. So we don't even have to evaluate from 1 to 2, although if you do, you'll see that you get another positive derivative pointing up towards 2. But since we know that this has to be a semi-stable solution, our answer is the only answer choice in here that is in between 0 and 1. And if you really needed to guess on this, we know that any initial conditions that start below 0 can never make it past 0, because by definition, if you reach 0, you're no longer moving along y, your y prime is equal to 0, so your slope is 0. So no way that this thing can reach 1. And likewise, no way that something above 2 can ever reach all the way down. So A and D are automatically no good. And so 8 is B. 9. Let's find a suitable form for y of t using undetermined coefficients. Let's solve our characteristic solution, or characteristic equation. I say that wrong every single time. R squared plus 1 is equal to 0. So this has roots of plus or minus I, so yc will be c1 cosine t plus c2 sine t. So what we would have liked our solution to be here, if I write it out, would be, let's see, we have to split our t up into some constant times t plus some constant, so at plus b plus, and then we have to do the same thing with this t, ct plus d sine t plus et plus f cosine t. There we go. But since we see that this guess, this is our guess for y particular of t, we see that this guess has some constant times cosine and some constant times sine in it, and our solution for the characteristic equation has some constant times cosine and some constant times sine. If we multiply both of these by t, we will no longer have that problem. So the answer that we are looking at is right here, answer choice A. And it's important to recognize that C is only incorrect because you need CT and D, say, for cosine, but then you need a different set of constants for sine. There's no reason why sine should have exactly the same constants on it. We can't tell at this point. So 9 is A. 10, a weird one. Let's determine the values of alpha such that all solutions of the following equation tend to 0 as t approaches infinity. So we know that, let's see, if our solution for our characteristic equation gives us, let's see, if our yc is c1 e to the negative something, I'll use d1, sure, d1, not lambda, d1t plus c2 e to the negative d2t, that our solutions will approach 0 as time approaches infinity. And all I'm really going for here is to show that no matter what constants we have out here, if the sign on our t up here, okay, I gotta be, if I want to be actually rigorous, I gotta say like d1 and d2 are greater than 0, whatever. I hurt myself trying to go through this whole thing, but I hope you see what I'm getting at. So if our solutions for our characteristic equation are negative, then our solutions will approach 0 as t approaches infinity. You can plug in infinity into these t's, and you'll get 0 as your output. So let's solve our characteristic equation. That's just going to be negative b, so 2 alpha minus 1, over 2, because we have to divide by 2a, over 2. And then it doesn't actually matter what the rest of our equation is, because this is going to be the real part of our solution no matter what. And no, I should actually evaluate the rest. I think I'm being wrong here, but let's make sure, because if this component, this big square root over 2, ends up being negative in here, then we're still good, because all that means is that our origin is acting as a spiral sink. It's still a sink. We're happy as long as it's a sink. we just don't want a saddle point to deal with here. Okay, so we will have in here b squared, so that would be 4 alpha squared minus 4 alpha plus 1, and then minus 4ac, so minus 4 alpha squared plus 4 alpha plus 4, yeah, minus 4 minus 4 times a times c. Oh, that's minus 4. Yeah, so we get these two alpha components cancel, and we get negative, if I'm correct, it looks weird, but negative 3 in there, which is, as I was saying, perfectly fine. That will just contribute some rotation to our solution as they kind of spiral down the drain back into the origin as t approaches infinity. And this component right here will always be negative so long as alpha is less than 1/2. So 10 is e. Suppose u of t is given right there, and it's the solution to a mass spring system's motion. What are the period and amplitude of u of t? So we know that the period, which I'll just call p, is 2 pi over whatever is multiplied by t in here. So we get, I don't need another equals, we just get 2 pi over 3. And that our amplitude is the square root of a squared plus, oh, I shouldn't really be using a in here. And I bet that bugs some of you, but that's fine. C squared plus b squared, where we'll call, excuse me, this term in front of sine c, and this one b. You could also just recognize that 3 and 4, if you're into really cutting little bits of time off your exam, that this is a Pythagorean triple, so we'll get 9 plus 16, so 5, and our answer is C. 11 is C. 12, because y equals t to the negative 1 is a solution to this, we're looking for a second solution by reduction of order. What would that be? Well, reduction of order says that y2 is equal to y1, which is t to the negative 1, so t to the negative 1 times the integral of this rational expression, e to the negative integral of p of t dt over y1 squared dt. And we know whenever we're looking for a p of t, which is going to be, in this case, the term on our y prime when the coefficient on y double prime is 1, so dividing out a t squared from all of this, we will get 3 over t, yeah, 3 over t. So we are solving this guy right here. We can replace this y1 with a t to the negative 1 squared, so t to the negative 2. That can come up here as a t squared. And solving here, we will get 3 ln t. We can replace this e with that t, and we are left with t squared over t cubed, so we get 1 over t dt, and they're looking for the function that we're multiplying by t to the negative first power to get y2. So as a result, it's just the result of this integral here, so ln t is our answer for 12, that's B. 13, I actually completely and utterly failed to factor this equation, getting the characteristic equation of 4r to the fourth minus 5r squared minus 9 equals 0. I could not factor that a second ago. So because I have a whole nother exam to record tonight, you get to hear me shamelessly type this into symbolab.com. So 4x to the fourth minus 5x squared minus 9 is equal to 0. Oh wait, I forgot to tell it to do something with it. Oh no, it still did it. So we see that x is equal to plus or minus, wait, we're not x anymore, we're r r is plus or minus 3 over 2 and plus or minus I. And so as a result, our fundamental set of solutions will be e to the 3t, e to the negative 3t, and then our cosine and sine, which is just pretty basic. So 13 is C. The basic part is everything but the factorization, which I'm sure I would slave over and get during the exam, but I can't be bothered right now. 14, on the other hand, this one is an absolute, I don't know. I've done it a couple times, so I know how to go through it. It's not knowing how to go through it that's the problem, though. It's the integrals that are the problem. So let us begin. We're using variation of parameters. Oh, I'm so excited. We can divide, we're going to need to divide a 2t squared out of everything, because one of the terms that we need for this is f of t, which is the right side of our expression, so long as the coefficient on our highest y double prime term is equal to 1. So this will just be 2 plus 2 over, that looks too much like a t, 2 plus 2 over t. There we go. Additionally, we're given our fundamental solutions. y1 is equal to t. No, it's not. It's equal to root t. y2 is equal to 1 over t. And then what is the final thing we need? We need the Wronskian of these two solutions, which is t to the 1/2 and its first derivative. So negative 1/2 t to the negative 1/2, and that's wrong. It's plus. There we go. And then 1 over t and negative 1 over t squared. You can already see how disgusting this is going to get. Not this determinant, but this is giving you an idea of what we've got coming up. So this is, I'll rewrite this as negative t to the negative 2, and this as t to the negative 1, just to make things a little easier. So we get negative t to the negative 3/2 minus 1/2 times t to the negative 3/2. So in the end, we get a Wronskian of negative 3/2 times t to the negative 3/2. Awesome. Okay, setting up our solution, we will have that y of t is equal to negative y1, so negative t to the 1/2 times the integral of y2, which is 1 over t multiplied by f of t, which was 2 plus 2 over t. All of that is divided by our Wronskian, negative 3/2 t to the negative 3/2 dt, and then we're adding y2, 1 over t times the enormous integral. We still have the negative 3/2 t e to the negative 3, nope, there's no t there, thank God. Negative 3/2 t to the negative 3/2. And then on top, instead of y2, we have y1, which is t to the 1/2, and we're multiplying that by f of t yet again, so 2 plus 2 over t. Okay, let the great simplification begin. We can take this factor of negative 3 over 2 on the bottom and bring it up as a positive 3 over 2 on the top, because we had a negative sign to cancel it out with. And by 3 over 2, careful, I mean 2 over 3. Likewise, this negative 3 over 2 will come up as a negative 2 over 3, like that. And then what else can we do? Well, this 1 over t can come down here. This t to the 3/2 can go up there, and then we can subtract 1 from that exponent, and now things are looking a little better in that integral's world. Additionally, this negative 3 over 2 can come up and make this a t squared. So to make sure, and this is plus 2 over t, there we go. To make sure I don't mess up anything now, I am going to take these integrals individually down here and deal with them. So we have the integral of 2, and I wrote a t. We have 2 t to the 1/2 And then 2t to the negative 1 times t to the 1/2, so plus 2t to the negative 1/2 dt. This is a snazzy looking integral. It's pretty cool. And then over here, just taking this integral, there we go. Taking this integral down, we have the integral of t squared plus, 2t squared plus 2t dt. Let's compute the easy looking one first. This will give us, I need some space. We'll bring this constant back into things. So negative 2 over 3t multiplied by 2/3 t cubed plus t squared. Okay, great. That half is done. Now we have the slightly uglier half to deal with. We will have 2/3 t to the 1/2 multiplied by the result of this integral, and then we're subtracting these two, and we will eventually get an answer out of this. So this integral, the integral of 2t to the negative 1/2 will be 2t to the 3/2 times 2/3, so we get 4 over 3, 8 over 9. Okay, yeah, that's looking good. And then here we will get plus 2t to the 1/2 times 2, so that's 4. 8 over 3. Okay, I think we're good at this point. So one final simplification step, we can factor both of these outer terms in, and we will get 8 over 9 t squared plus 8 over 3 t, and then we're subtracting from that whatever this is, which is 4 over 9 t squared. There's our answer, by the way. 4 over 9 t squared plus 2/3 t. Okay, yes, it all works. So computing this, we will get 4/9 t squared, and then 8 over 3 minus 2 over 3 is 6 over 3 plus 2t. Oh, God. And we're finding the whole general solution, so we have to add in C1 and C2 times our fundamental solutions to the homogeneous equation. Okay, 14 is A. Phew. That's by far the hardest thing on this exam. So now that we're done with that, we are theoretically slightly in the clear. Let's find the inverse Laplace transform of this function. I'm going to grab, oh, no, that's a linear exam. There we go. I'm grabbing us the cheat sheet, the legal cheat sheet, and we are going to find this, we're going to find this inverse Laplace transform. So we know that multiplying something we're trying to take the inverse Laplace transform of by e to the negative cs will do this. So instead of just finding the inverse Laplace transform of this normally, we'll kind of do that. We'll find the inverse Laplace transform of everything else normally, multiply it by uc of t, which in our case is u3 of t. So we know that our solution will begin with u3 of t, and then we'll replace all of the t's that we get from the inverse Laplace transform of this with t minus that c value, so t minus 3. So right off the bat, we can get rid of option C because it obviously does not replace all of its t's with t minus 3. Neither does B or E. They just add a negative 3 in here, where if you really put the t minus 3, you would get a t minus 6, or a 2t minus 6 in there. So now all we have to deal with is a partial fraction. Whoop. That's not what I meant to do. There we go. That's the only time. That's the only time in like 50 hours of recording that I've ever left the exam by accident. That's wow, you just witnessed extremely minor history there. So now that we know really the roadmap of what we're doing here, we're going to have to pull a little bit of trickery with this denominator here, or well, this whole section of the expression. So we can express this as alpha plus 1 over alpha minus 4 squared. That's going to contribute our alpha squared minus 8 alpha plus 16, and then we'll have to add a plus 2 squared there as well. So, okay, we actually don't have to do any partial fractions. That's nice, because we can split this up into a plus 1 over alpha minus 4 squared plus 2 squared. Multiply this by 2 and 1/2 outside. And, ooh, I actually did that slightly wrong, but it's in an important enough wrong way that I'll have to go back and show you what happened. So what we're going for here is we're going for using the e to the at sine bt and the e to the at cosine bt formulae. So we're going to put our expression into this form right here. It's just how we go about doing that. That's the question. So we have an alpha plus 1 up here. We want an alpha minus 4. Alpha minus 4. So if we turn this into a minus 4, we've subtracted 5, so we'll need to add a 5 over alpha minus 4 squared plus 2 squared. But then up top here, we only want to have a 2, because this expression, if we have b squared down here, it wants b up top. So getting b up top is a matter of multiplying what? By, well, if we have a 2 up here, we'll need to multiply by 5 over 2 to get that back. So now we can really just go take our answer right out of this. So we know that this thing will turn into e to the at, where a is the value we're subtracting from here and here. So e to the 4, but instead of t, we're writing t minus the c value, so t minus 3 cosine of 2t, but instead of t, we're writing 2t minus 3. And then we are adding 5/2, which is just the factor that we had to pull out here, e to the 4 t minus 3 sine of 2t minus 3, and that, forgot a parentheses, that should be good, and we'll see that evaluates pretty nicely to answer D for 15. 16, what's the solution to this initial value problem? So hopefully you know this already, because I'm getting a little tired of writing it out, is the Laplace transform of y double prime. That's going to be alpha squared y subscript alpha minus alpha times y at 0 minus y prime at 0. And the Laplace transform of y prime is alpha y at alpha minus y at 0. And the Laplace transform of y is y at, no, it's not y at 0, it's y subscript alpha, at least the way I write things out. So let's take the Laplace transform of both sides of our equation here. That gives us, and I'm actually going to do that up here, because I'm afraid this might be a big scary one to solve. So this y double prime will become alpha squared y alpha minus alpha y at 0, so that's plus alpha using that initial condition, minus 4 using that initial condition. And then we're adding 4y alpha, and that's equal to capital G of alpha, which is just the Laplace transform of g of t, just like how the Laplace transform of f of t is capital F of alpha. They write it f of s. I'm in the anti-s camp over here. So let's solve this for y alpha. We can add 4 over here and subtract alpha. That gets rid of those two. And then divide everything by alpha squared plus 4, factoring those out from our left side, and we're left with y alpha. And let's split this up into 4 different terms, and we should be able to directly solve for these. This isn't what's it called? Partial fractions case. So y at alpha is equal to g of alpha multiplied by 1 over alpha squared plus 4. I'll switch this up a bit to 2 times 1/2 so that this is in the form of something that we know how to take the Laplace transform of. Then we will get plus 4 over alpha squared plus 4. I'll change this to a 2 times 2 there. And then what else? We have minus alpha over alpha squared plus 4. So all of these are in the form, in a nice form that we can take the inverse Laplace transform of. Because we have this unknown function g and it's multiplied by something that we do know the inverse Laplace transform of this, and even though g is unknown, we know it's inverse Laplace transform because we took the Laplace transform of g of t to get there in the first place. So we'll be able to write y of t right out as the integral from 0 to t of f at t minus tau. So what's the inverse Laplace transform of this? This will just be 1/2 sine 2 t minus tau, plugging in t minus tau for all of our t's here, and then multiplied by g of tau. That's a nice looking tau. I'm liking that tau. G of tau d tau, and that's it for that. And then all we're left with is plus 2 sine 2t minus cosine 2t. And where is that? That looks like answer choice D for 16. 17, let's find the Laplace transform of this unit step function-y looking thing. So between 0 and 1, we want f of t to be equal to t, so let's just put a t out there. And then let's add u1 of t. So remember, the unit step function is a function that's equal to 0 for all t less than whatever it has in this subscript here. And then at that value, in this case 1, it will jump up to y is equal to 1 and stay there for all of the rest of the t's. So we can use this as kind of a switch that turns on at t is equal to 1. So u1 of t multiplied by, actually let's subtract it here and say t minus 1. So there we go. When t is less than, greater than or equal to 0 and less than 1, this thing will be off. So we'll just evaluate to t, and when t is greater than or equal to 1, we will get t minus t plus 1, and so that'll evaluate to our 1. And this is kind of the game that we're always trying to play with finding Laplace transforms with unit step functions. We always want our unit step function to be multiplied by some function of t, where instead of t, we have t minus this c value for all of our t's. And here, this t is matched up with a t minus 1, so we are good, and we can take that Laplace transform, and the Laplace transform of t will just be 1 over alpha squared. So f of alpha will be 1 over alpha squared minus e to the negative alpha, that c value as 1 going up into the e to the negative 1s up here. And then we have the Laplace transform of f of t. So this is f of t minus c, so we need to get rid of that negative 1, and we already know that the Laplace transform of t is 1 over alpha squared. So we get 1 minus e to the negative alpha over alpha squared. 17 is B. Okay, we made it, guys. We made it out of Laplace land, and we have technically an hour and 4 minutes left in this exam, but I've done this one too many times for it to be real. Although I would say, excuse me, after that burp, that this exam seems to be by far the easiest of all of them. And I haven't really gotten a good sense for what's the easiest because I don't do these often enough. But now that I'm doing so many a day, this is I think my 4th exam I've recorded today. This one's super easy. So if you want an easy exam, you pick the right one. The phase portrait of this system is what? So that's all based on the type and sign of the eigenvalues of this matrix A here. So let's find those. Let's solve -2 minus lambda times -4 minus lambda minus 3 is equal to 0, lambda squared plus 6 lambda plus 8 minus 3 is plus 5, lambda plus 5, lambda plus 1 is equal to 0. And because lambda is equal to -5 and -1, those are our eigenvalues. We have two negative eigenvalues. What that means, and we kind of saw it earlier in one of those other questions, is that our solutions will radially flow in to 0 as t approaches infinity, like so. So that makes our origin nothing to do with spirals. We don't have a plus eigenvalue and a minus eigenvalue, so it's not a saddle point, and it's not an unstable node. It's an asymptotically stable node. You can think of it as what I keep saying is like a depression in a trampoline, or if you pull down on the middle of the trampoline, things would don't think of the spiral though, because the minute you think spiral, then we got complex things going on. But yeah, they flow into the origin as time goes on. If you had the opposite, you pushed up the center, that's the same thing as our two positive eigenvalues. That would give us an unstable node. If you put anything around the vicinity of the origin, they will flow radially away from the origin as t approaches infinity. So 18 is A. 19, let's find the general solution to this clearly multiple eigenvalue having matrix right here, because we have t's and then a generalized eigenvector to worry about. So -4 minus lambda times -8 minus lambda plus 4 is equal to 0. Lambda squared plus 12 lambda plus 36 is equal to 0. Lambda plus 6 squared is equal to 0. Lambda is equal to -6 with a multiplicity of 2. So plugging in lambda equals -6 to a minus lambda I, we will get 2, 4, -1, -2. We can simplify this down to 1, 2, 0, 0, and extract an eigenvalue of -2, 1 out of that, because we can write this as an equation. Because we're solving a minus lambda I equal to 0, we can say that x1 plus x2 is equal to 0. x1 is, plus 2x2 is equal to 0. So x1 is equal to -2x2. And since we're writing a vector in terms of x2, because that's our free variable, x2 is equal to, -2x2 is equal to x1, and 1x2 is equal to itself, which is just x2. So there is our first eigenvector. So we can start writing, that's a y, I wanted an x. We can start writing x of t, which is our solution. That'll be c1, y1, e to the lambda 1t plus c2, and then double bracket time y1 multiplied by t, and then we need to add a generalized eigenvector e to the -6 t. And that generalized eigenvector will come from solving a minus lambda I set equal to our first eigenvector. So 2, 4, -2, -1, -2, 1. We can use our first row to set our second row equal to 0. So let's just go through and, do that. Although I'm not going to be that quick to do that, just because we have, even though, that works. No, I'm just doing that. I'm just getting thrown off because there are a couple answer choices in here that have components for both of these, which you'll see that we do not get. So we know that A and D are false. And now all we have to do is divide this by 2, and once we get, as long as you're doing this the same way that I do, as soon as we get the 4 components on the left side over here equal to what we had the four components in A minus lambda I when we solved for our first eigenvector, this right side is our generalized eigenvector. So as a result, we can replace this with -1, 0. And it looks like what they've done here is been a little rude and flipped the sign on absolutely everything in the answer that we found, which is in the end perfectly fine because this constant can be positive or negative to compensate. So 19 is E, and I guess we'll give them that one. So we have a 2 by 2 matrix here with some complex eigenvalues, and they give us an eigenvalue-eigenvector pair. And we're told that this non-homogeneous system here has this guy as a solution. We're finding the general solution. So all we need to do is take our known eigenvector 1 minus 1 minus I and multiply it by e to the lambda t. So here is our lambda, and multiplying that by t, we can expand that to -2t and e to the it, because this would be, we would have e to the parentheses -2 plus I end parentheses times t. We can split that off into this, and that's important because we'll take this e to the it and replace it with cosine of t plus I sine of t, just like that. And then the sine and cosine portion of our solution, we can get rid of this, the sine and cosine portion of our solution will be the real and imaginary bits that we get from expanding this expression. So I'll start writing our solution. X of t is equal to c1 times the real vector. Well, we're going to get a real value when we multiply cosine on top, so cosine of t, and then we'll get a real value when we multiply cosine to that -1 on the bottom, so negative cosine of t, and when we multiply I sine of t to the negative I there, so we'll get plus sine of t e to the -2t, still using that real bit, the real portion of that e that we're left with. And then we're adding c2, and this will be, this vector will be composed of all the imaginary bits. So I sine on top, we drop the I, we're left with sine t, because the whole point is to make this solution real, so it's not rigorous to think about, like not mathematically rigorous, but we're trying to get rid of that I, so we just drop the I at this stage. And then what about the bottom? How are we going to get an imaginary value? Well, if we multiply cosine into that negative I, we'll get negative cosine of t. That's weird. Cosine of t. And if we multiply I into this -1, we'll get negative sine of t. And so now adding on this portion of the solution plus 1, 2, e to the -2t, which we totally could have solved for. Yeah, we could have totally done that. They just didn't want us to. Not particularly sure why, but I'm okay with it. And we should have our solution here, which cosine plus sine minus cosine, sine minus cosine, 1, 2. Yeah, okay, so B is our solution for 20. Okay, there we go. Pretty easy exam, except for that one pretty brutal variation of parameters question. And that's about it from me.